Thank you, Jason, and thank you for having me here today. This is the company Zerronox Corporation, and we're using high-powered pulse electron beams for the removal of nitrogen oxides and other emissions from power plants. So I'll start off with a little bit on my background and the team we have at the Naval Research Laboratory in Washington, D.C., and then get into the value proposition of our technology, a little bit on our pulse electron beam technology itself, and then summary, and then next steps from there. So my background is in engineering and business, and I primarily focus on the business side of things. And historically, over the last 20 years, it's been a very early stage technology, sometimes just one or two PhD founders that have really creative technology. I lead the business side of the company, develop the plans, the finances, interface with the investors, and then build out the management team of the company and help scale the organization. And so I look for what I call transformational technologies with a value proposition of at least 10x over the existing conventional technology, 10x primarily in economic terms. And so some of these companies have had value propositions of closer to 100x, but if you can go 10x, then that's a nice starting point. I also look for companies that have strong competitive advantages, including patents, and or where you can leverage Moore's law, where you're seeing a doubling of an improvement in the economics every 2 years, or where you can create switching costs. And one of the switching costs is called a network effect. And this is something coined by Robert Metcalfe in the early 1980s. And essentially what he said was that the value of a network is proportional to the number of connected users. It's actually proportional to the square, so it's exponential in nature. And you've seen this in the telephone. You've seen it with your email. So the more people that are connected, the more valuable the network becomes. Today, a lot of software companies leverage this, such as Facebook, and where they get, as more and more people connect to their site, then you reach sort of a tipping point. And tipping point is usually about 20 to 40% of the users, and then everybody starts using that website. Jason mentioned that one of the things that he found intriguing was how you can take technology that was developed for one application and then apply it to other applications. And I'll get into what we're doing now with Zerronox. But earlier, a couple other companies. One was Simpel Corporation, and this is a team of very high-level engineers from Jet Propulsion Laboratory in Pasadena, California, and they had very high-end MEMS, which is microelectrical mechanical systems. Sensors, and these were for military applications. And so we started off in the optical switch market, but at the same time, we saw the advent of the smartphone coming. And so we said, well, this looks like a much more attractive market to us because there's no one else looking at this market. And so we transitioned the company from military applications to the optical switch for telecom to a smartphone. And what we were doing with the smartphone is we totally redesigned the camera module itself using this technology. And we were able to shrink it down by a factor of about 100 from the older technology. In a similar situation, Picolite, the gentleman from Bell Labs, very well-known PhD engineer, had written in Scientific American several articles, and they were developing at Bell Labs what they called an optical computer. Now this is in the late 1980s that they were looking at optical computers. So there were no wires, there was no electricity. But to do that, he knew that you have to get electricity to the computer somehow. So he made this really, really small switch from electrical signal to an optical signal. And so he was able to shrink the size down by a factor, once again, of about 100 from the existing technology. The older technology was a laser that was an edge-emitting laser, and this new technology was a surface-emitting laser. And so not only was it smaller, but it coupled into the fiber optic line much better. So we took this company from, it was just the two of us, Boulder-based company, and took it to more than 100 million in revenue, and then sold it to JDS Uniphase. So those are just a few of the companies. I won't go into the other ones. High-speed wireless, displacing silicon. You'll hear more and more about gallium arsenide and indium phosphide in the future, I'm sure. I started actually with a environmental company, a clean tech company, right out of business school. And my background is in engineering and in business, as I said at the very beginning. The lead on our technical side, he was at the Naval Research Lab his entire career, John Sethian. He was the original developer of this pulse electron beam technology. It wasn't used for what we're using it for. It was developed to drive lasers for a fusion process. And they had invested, they being the Naval Research Laboratory and government, through government funding, more than $150 million over 15 years to do this. He's won several awards, and his background is in applied physics. Here's our team from the Naval Research Laboratory. We have about half a dozen people that are regular on our team. Additionally, off-site, we have Silicon Power to help us build the advanced solid-state power system itself. At the NRL, there's more than 2,000 employees, with 750 of them being, PhD level engineers. And so with that, they have, you have chemistry, mechanics, and you also have computer modeling, which is really important because we can model everything in advance of actually testing it. So what's the genesis of this project, or the PEB approach for emission control? About 2 to 3 years ago, a colleague of mine at a Wyoming-based power plant, he said, he knew my background, he said, Steve, I know you look try to looking at, really far out, high-end, advanced technologies. We're going to be seeing, millions and millions of dollars, hundreds of millions of dollars for emission control. So if you can find something, take a look. And I looked considerably for 2 to 3 or 6 months, and then I found a paper written by the Naval Research Lab for using their pulse electron beam technology to remove nitrogen oxides. So that was the genesis of the project. You're very familiar with the regional haze rule. I don't need to go into that. It's driving the NOx emissions, and of course for CO2, it's a clean power plan. And so with the clean power plan, they're looking at, here in Wyoming, is my understanding, a 44% reduction within the next 7 to 8 years. So what intrigued me about the pulse electron beam technology is that it uses a very elegant physics approach rather than a chemistry approach. And so the analog would be an incandescent light bulb versus a fluorescent light bulb. In the fluorescent light bulb, which is what we're using, virtually all of the energy goes into, on the right here, goes into the light itself. Whereas on the left, the incandescent, as we all grew up, touching the light bulb, even after we turned it off, it was very hot. So a lot of the energy was wasted and it went into heat. The conventional, I'm going to compare what we're doing versus conventional removal technologies. The NOx removal, it uses SCR, selective catalytic reduction. It's more like the incandescent light bulb. It does work. It is complex. Uses it's a chemical process. It's fairly expensive for a typical, say, a 500 to 600 megawatt power plant. You're estimating 200 to 250 million in capital, and about 20 to 25 million in annual operating costs. So we can come in. Our value proposition is about 5x or 1/5 the cost in capital over the SCR, excuse me, and about 1/6 to 1/8 the cost in annual operating costs. Okay, to summarize a little bit more about the pulse electron beam, so it's what I consider a platform technology. It can be used for a number of different removal applications, not just NOx removal. It does have, a significant cost advantages. Over the conventional technology. It doesn't use any catalysts or reagents, and there's no waste or byproducts. And it can be used on virtually any fossil fuel application. As I mentioned, it's a platform technology, so we've shown that it does remove not only the nitrogen oxides, which we've optimized the process for, but it also for the sulfur oxides, without even optimizing it, it removes up to like 50%, and we can oxidize mercury for the ease of its removal. We haven't done much work yet on CO2. We'd like to pursue that very intensely over the next couple years, but some preliminary testing have shown that we can reduce it from 15 to 30%, and with the generation of some synthetic fuels that can be rerouted to the boiler. And the estimated power requirements for NOx removal, first of all, for like 80% removal would be about 2 to 3% of the plant's power. And for CO2, we're estimating, or actually it's more of a goal, but it would, for 30% reduction, would be about 10% of the plant's power. This is just a short comparison of what I just, or a summary, a chart of what I just went through. So I won't go too much into the technology, but this is, so it's a double-sided approach. This is the main parts of the electron beam itself. You can see in the center is a reaction chamber, continuous flow of the flue gas up through the chamber. We have the pulse power systems coming in on the blue from both sides. It goes through a cathode that's driven through the anode to the reaction chamber itself. And the way this would work is that as I mentioned, the flue gas flows continuously past the reaction chamber. The electron beam, even, we show 3 steps, but once again, just keep in mind that it's continuous flow. The electron beam deposits its energy into from both sides into the chamber itself. It cleans up the gas, and then another slug or another fill of gas comes up, and then it does that again. So the reaction chamber, it has hundreds of billions of watts of power, and all of this is delivered in less than 1/1,000,000th of a second, if you can imagine. It's actually 1/10 of 1/1,000,000th of a second, or about 100 nanoseconds. The residence time within the flue gas itself is about 1/10 of a second. So there's about a factor of 1,000,000 to 1. So the way to look at this is that essentially what you're doing is just taking a picture. It's that fast relative to when you're comparing the length of the pulse itself to the residence time of the gas in the flue. And we're running this at 5 hertz or 5 times per second. So to make sure that we are optimizing the process, studies have shown that the optimal amount of energy for us, to minimize the amount of energy, is to do it in the shortest amount of time and this will convert as many of the nitrogen molecules into nitrogen atoms. And that's what we want to do. So the higher the concentration of nitrogen atoms, the faster the removal rate of the NOx. So in the ideal situation, you would have a single short pulse as opposed to a long or continuous pulse. And the reason I mention this is because about 10 to 15 years ago, there was some technology that came out of Japan that was a continuous E-beam, and this is why it didn't work, and it just couldn't compete economically because they didn't really fully understand the advantages of pulsing the electrons. As I mentioned, we have a double-sided exposure for uniform deposition. It's modular in design, and so we can fit any size power plant from like 50 megawatts up to 500, 800 megawatts. The reaction chamber itself would be about 3.5 meters by 0.5 meter by just a little bit less than 2 meters. So this is some actual graphical showing what I just mentioned about the advantages of a single pulse versus multiple pulse. You see the single pulse is in the blue diamond, and on the left axis is the final NOx concentration, and the bottom axis is the amount of energy that's been deposited. At the same time, this shows that the short pulse is more advantageous than a long pulse. This is the actual test center at the Naval Research Laboratory for our experiments. And this is where we've done, all of our optimization work for using the actual flue gas from a power plant for the nitrogen oxide removal. And as you can see, there's a ladder in the sort of off to the left there, and that ladder gives you just an idea of how big this is. On the two sides are the pulse power systems, and in the middle is the electron beam source and the reaction chamber. And then rather than to simulate a continuous flow of gas, we use a gas recirculator. So the next steps for us are to, the end goal here is to actually commercialize this. The Naval Research Laboratory has been, working closely with us, and they really want to see this technology commercialized. They think it has a lot of potential. There are some other applications outside of what we're doing for emission removal, but nonetheless, they really want to see it commercialized. So what we would like to do is to, optimize it for the other emission pollution products themselves, such as sulfur oxides and mercury, focus intensely on CO2 and optimize that process. I have one possible path for CO2 abatement where we would ionize the CO2 molecules, and then we could use, we have time in between the pulses to add catalyst reagents, and this would, and then with the reagents we could react it with hydrogen and form synthetic fuels that would be redirected to the boiler. So this is just one possible pathway. We have probably half a dozen that we can explore. So the next steps for us, we'd like to also, in conjunction or in parallel with, the optimization of these other removal technologies, would be to build a prototype over the next couple of years that would treat about 3 to 5 megawatts of the flue gas. The dimensions of this prototype would be about 40 feet by 8 feet by 10 feet. It would be about 1/18th the scale of one full system, and we would need about 10 to 12 full systems to build for like a 500 to 600 megawatt plant, if you followed those numbers. So it'd be like 1/18th, so it'd be what 1/200th. You need to be about 200 of these prototypes to treat about 500 megawatts, in other words. So the next steps, as I mentioned, build the prototype, CO2 process development, continue on our market development efforts and commercialization efforts. We have had discussions about relocating the company to Wyoming. We believe that this would be an ideal place for our organization, and where we would be using Wyoming resources where possible, both with the power plants and with the talents that there are at the University of Wyoming and with the various organizations within the state. That's it. Thank you very much. Should I open it up for questions? Or?
Yeah.
Okay.
Thanks for the presentation, Steve. From the perspective of, kind of on the heels of the governor's announcement on the integrated test center and being able to provide a place for us so that people could come in and get some flue gas and see what they can do. If Wyoming and industry, people that are involved in coal, wanting to help the governor's vision become a reality, what sort of dollars are in play in the that's necessary out there to support these technologies and to bring them in? If you were looking at, for instance, the ITC operating entity, and one of its jobs was to vet technologies and align technologies and capital to try to, do this.
Well,
what kind of dollars are we talking about to try to,
Well, for us to commercialize, thank you for the question. Did everybody hear the question? Okay. For us, the two things that we're looking at, primarily CO2 and then the prototype. The CO2, we would probably be requiring $5 million a year for 2 years to really, hit it hard and make sure that we exhausted all the possible resources we have at the Naval Research Laboratory, and also at the, within the state of Wyoming at the SER. And to build the prototype, that would probably be an additional $15 to $20 million to build this prototype. Then you would have to commercialize it. I think at that stage, once you've proven CO2, we've got a technology that's very efficient, that works, that everybody acknowledges, could be as Governor Meade said, a game changer for the state and for the U.S. and potentially for the world. Then you would probably go to the private equity markets, which is my background, and raise funding through those sources. I have been in touch with a number of private equity firms who are very interested in what we're doing here, but they want to see it, as I said, they want to see it working prior to investing their funds. But there's billions of dollars of private equity funding available for advanced technology such as this. Did that answer your question?
Thanks, Steve.
Do we have any other questions? Well, Steve, thank you very much.
Okay. Thank you again.